Well, guys, we're coming up towards the end of the semester. The last sections we're going to have, last videos. I want to talk about climate, and I'm going to talk about some of the implications, including weathering, and we'll be done for the semester. The last of the quizzes will be due at the time of the final exam. So, pay attention, we'll get this done, and you can get on with your life. It's strange times we're living in, but it won't last forever. Hope you're doing well. Okay, so you'll hear the term climate change an awful lot. It was sort of started because people didn't want to talk about global warming because it became too political. Well, climate change has become very political as well. And that's just the reality of the times that we live in. Just like Hurricane Katrina, where we knew things ahead of time but didn't prepare, we may be looking at changes to the climate that we're not prepared for also. So what I'll make for you today is the case that we do know quite a bit. There's not nearly the controversy that some of you believe, and that we can do something about it. Okay, we've talked about the scientific method before, so we have observation and explanation, some predictions, and some interventions. I'll just give an example of mental illness in my family. That's observation, pretty common. Back in the old days, we might have explained it by evil spirits. Nowadays, we might explain it by biochemistry or upbringing or environment or something like that. We could then take those explanations, do something, and then see whether or not it had the desired effect, which should be eliminating the problem. So we might try an exorcism if we think it's an evil spirit. We might try burning the person at the stake. That would certainly get rid of the problem, but not a solution I would support. And we might try some sort of biochemical like Prozac or Paxil or one of the other ones that are very common these days. Then we can look to see whether or not that intervention made a difference that we had hoped, and decide if that's something we want to continue to do in the future. Right? Scientific method. So I'm going to follow some of that same thing today, but I want to tell you where I'm going with the talk. The first thing is there's very little disagreement that the climate is warming. Almost everybody knows that simply because the data is so strong. We've been measuring for a long time. We've got lots of data, and I'll walk you through some of that, but there's plenty of evidence that the climate is getting warmer. There's a lot of evidence that the humans are accelerating that warming, that we're one of the main causes for recent uptick in terms of temperatures. But that's where a lot of the political controversy comes along. And then the last point, our response is an ethical decision. That's where it really tends to get very political very fast. That's the should question. Should we do something or not about global warming? Right? Values sort of issue. We'll end there. So in terms of the scientific question of whether or not the climate is warming, some of the things we might look at is direct measurements of temperature, some indirect measurements of things that might be affected by changes in temperature, some proxy data, which are things we could measure that indicate the change in the temperature. We might try to ask ourselves what time frame we're talking about. Is it recent? Is it really eons? What do we mean when we say the climate is warming? And then, is what's occurring upward trend, or is it just a fluctuation? And are the measurements we're taking biased by a variety of things we haven't accounted for? So that's what we're going through. So first, the time frame. If we talk about warming, we might say it's warmer at midday, but it was colder last night. It's warmer last summer, but it's colder 200 years ago. Colder 20,000 years ago, back at the end of the Ice Age. It was warmer 130,000 years ago when it was in the middle between ice ages. Colder 1 million years ago. Warmer 5 million. Warmer, a lot warmer 4.5 billion years ago. You get my point. So we're always talking about a time frame over which the change has taken place. It's not even clear sometimes what average means. Typically, when we're talking about average temperatures, we're talking about the average in terms of the maximum plus the minimum divided by 2, just the average of those two. But that may or may not really represent what the average is during the day. I'll look at Dubuque in the left-hand column here, Las Vegas in the right-hand column. We see a much bigger range, both in terms of the seasons, but also in terms of the day, in terms of the temperature. Dry tends to get, like in Las Vegas, tends to get cooler at night compared to how hot it is during the daytime, so we tend to get bigger fluctuations, swings during the day. But we get a lot more seasonal variation in Dubuque. Okay, that's no shock, is it? Okay. How do we know what's happened way in the past when we don't have any measurements? Well, we look at the isotope data we talked about in the first part of the class. And what we can see is looking at carbon dioxide measurements for figuring out time and looking at oxygen isotopes figuring out temperature. Remember the isotope dance. What we can see real clearly is that in the last little bit since industrial revolution, the temperature has fluctuated and gone way up very quickly, right? But if you look a little further back in time, we see there's been these cycles up and down that have taken place, cooling and then warming, cooling, and now spiking up in terms of the temperature. So maybe if we're looking a longer term, we might say, oh, well, that's not that big a difference, right? Why are we all bent out of shape and worried about it? One thing I want to make real clear right here, though, is see this little part right here where my little hand thing is? That's where human civilization has developed. So we've built lots of infrastructure, ports, roads, cities along shorelines and stuff like that. We've built agricultural areas, those sort of things, and we've made the assumption that climate is pretty stable, which for most of the last 10,000 years it has been. It's only recently that it's shot up since the Industrial Revolution in the last couple hundred years. So that's why we're so worried about it, is human society has come to depend on temperature being fairly stable. So the fact that it was warmer thousands or millions of years ago, so that wasn't, humans weren't around to worry about it at that point. Our direct measurements date back into the middle 1800s, something like that, especially looking at boats, ships from ocean going, because ocean water tells you a lot about the currents that are there and the speed you can make going from, say, the U.S. to Great Britain. That would be an example. If you're in warm water in the Gulf Stream, you can make better progress going across the ocean than you can if you're in the cold water. Those sort of things. So we've got some direct measurements of temperature, and again we see those measurements going up. We have direct measurements of carbon dioxide dating until the late 1950s. Again, we see that fluctuation up and down, and it's even higher. It's continued since, I think this last was 10 years ago that I made the plot, but it's still on its way up. It's continued. We can also measure the ice extent, which is one of those things that tells us about the temperature. And we see that the ice extent has gotten smaller. Ice has melted back. And we have some indirect measurements, such as the melt time of some of the ice in areas, all sorts of different types of records on that. But what we see there is it's melted earlier. We've got a longer season in which the ice is melted. You've all seen me do the isotope dance at some point. That's a proxy measurement. We measure the isotope, but it tells us something about the temperature that's going on. So we're getting a variety of historical measurements. We can also measure, besides the ice core, sediment types, tree rings. So during warm, wet years, the tree grows more. During the colder or drier years, it's going to grow less. The kind of fossils we see in the mud at the bottom of lakes or at the bottom of the ocean depend on the temperature and environment in which they grew. We see in coral growth bands, just like in tree rings, there's something about the water temperature there. So all these things are telling us what the temperature was like in the past. That's the key point here. So now, what about trends? If you look at this, if these are our data points, just the recent ones here, are we looking at some sort of fluctuation up and down? Or are we looking at some sort of changed system? That's part of the controversy that's going on today. You'll hear people say, well, it's been warmer in the past, colder in the past. It's just going up and down, and so that's all that's going on right now. But there are others who say, no, this is unprecedented. It's going up in ways that it hasn't during the time of human civilization. How do we go about figuring out which one it is based on limited data? That's a tough nut to crack, isn't it? What about potential bias? Well, if you look at this graph, you can see the temperature in yellow of Tokyo, and it looks like it's rising faster than the temperature in black, blue, red, and purple of other cities in Japan. But actually what's going on is that we have built up Tokyo tremendously. It's grown far more than other cities. And when you build cities with tall buildings, lots of asphalt, dark surfaces, you tend to heat up that area. The wind doesn't blow through because it's blocked by the buildings. The dark surfaces absorb heat. And so it appears that the temperature has gone up even though it hasn't. That's a potential bias, but one of the ways we deal with that is by accounting for the urbanization, but also looking at ocean temperatures, because those ocean temperatures haven't been changed by the urban effect, the cities. So, on to point 2. Humans are most probably accelerating the warming. To understand this, you first need to understand something about the greenhouse effect. Basically, we live on a planet with a wonderful atmosphere that holds in the heat, kind of stabilizes things, not too hot, not too cold, so that we can grow and life's good. The light comes in, warms the surface, and the atmosphere traps the heat in close by so that we have a nice, comfortable place to live most of the time. The main greenhouse gases, carbon dioxide, methane, water vapor. There's also nitrous oxide as well, CFCs, a few other things, but these are the big 3. Well, the one that we have influenced the most is carbon dioxide by burning fossil fuels, oil and gas. So we put more carbon dioxide in the atmosphere, in a sense made the glass thicker up here on top of our Earth, so it traps in more heat. So that human effect has caused more of the heat to get trapped close to the surface. So how do we know that that's what's going on? Well, one of the key things that we do is we develop computer models. You can say, well, that's just a computer, but if you're going to shoot a weapon at an enemy, you better know a little bit about some basic models like momentum. How fast the shell comes out of the gun determines how far it goes, right? That's one of the variables, momentum. But according to this model, if all you counted for was momentum, it would just go right on out into space. That's not the way it works. Gravity pulls it down, right? So now you've got a second one, gravity, that's pulling on it. So now you can maybe aim your gun a little bit better. But that's not really quite right either, because you left out something really important. Left out frictional drag, shooting it through the atmosphere, and that's going to slow it down also. So if your goal is to shoot a weapon towards your enemy, you better account for all the variables so that you can then test it by shooting it to see if you hit your target, right? Well, that's what we do with computer models too. We try to figure out all the different variables that count in terms of making a prediction, and then we test to see what's going on. With the computer models, we do the same thing. We collect data, we determine the significant parameters, we then predict the future behavior, and we then look to see how well we did. And here's the key point on this. If we account for all that human CO2 that goes in the atmosphere, what we've observed and what our computer model predicts match up really well, the red and the black. But if we don't account for all that human effect, the two start to spread out. We don't hit our target. Humans add to the warming, and so that's what we've been observing. That's the key part. But what do we do about it? That's the ethical question, isn't it? It's the should question. Should we do anything? Why do we try? Why try? Are we capable? So let's take a real simple example we all understand. There's hunger in the world. These are the red hot spots have undernourishment, right? In the United States, we've got a problem with obesity. Too much fatty foods, right? Lots of places, over a third of the population is obese. So what do we do about this? Maybe we could send the food over, right? Well, it's a little bit more complicated than that, isn't it? Destroy their markets in the process, the kinds of food people eat. There's lots of issues that we want to take into account. How is the best way for us to help out? Right? A historical parallel is looking at soil loss. So when the first European settlers moved into the Dubuque areas, there was tremendous soil loss, lots of areas washing away. So during the Roosevelt administration during the 30s, we created a soil conservation service. And the approach we took to try to help farmers prevent soil loss was an educational approach. We educated people about ways of preserving their soil. We talked about that on the first week of class, about planting rows along the hillside, about grassy waterways, all those sort of things. And by educating farmers, we were able to radically reduce soil loss in the United States. So we should do the same thing when we're thinking about energy and we're thinking about climate change. How is it we make those decisions, right? And so we've talked about these. We've talked about a rights-based approach. An example is the Endangered Species Act. These are turkeys in my backyard. By early 1900s, every turkey in Iowa had been killed off, but we successfully reintroduced them, and we've been able to figure out a ways of preserving them so that they're doing very well right now. Whoops. We've also looked at utility-based approach, how to pay for things versus how much they cost. And so we make a decision in the case of the 1976 RCRA laws, which were for cleaning things up. We decided to exempt the oil industry so that because in the 70s, if you remember, oil prices were super high and we were really concerned about the oil industry in the United States. So we decided that adding more regulations didn't make sense at that time. Technology-based approach. Smokestack scrubbers were put in to keep sulfur out of the atmosphere because it was causing acid rain. You set a standard and then people figure out how to make a living, make money anyway. Right? We've gone through all three of these approaches previously. We need to look at that in terms of how we're going to deal with climate change, how to protect the vulnerable, how to balance the cost and the benefits, and what kind of technology we can set the standards for so that people can still meet their basic needs but also become safer over time. Okay, let's finish this off with more of a philosophical thing. Let us consider the way in which we spend our lives. That's Henry David Thoreau. Because ultimately it comes down, do we need some of the things that we spend money on, spend energy on, or is there a better way that will make life better for everyone, including ourselves? Okay, that's enough for right now. Hope you guys are doing well, and I'll look forward to talking to you in face.